Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is Bruce Toal. Bruce is CEO of Convey. Welcome, Bruce.
Well, thanks, Rich, and hello to all your subscribers, and thanks for having me.
Terrific. Well, hey, I'm here in Hamburg, and you're still back in the States, but I have some slides here. Do you want to go through those?
Yeah, sure would. I'll start off with just giving some background on Convey, and then I want to go into a little more detail about some news that we've announced about Graph 500 and why our architecture really shines there. All right, well, we'll start off with first slide introduction. So Convey Computer is we're the developer of the HC1, which is a hybrid core computing system, and we'll explain a little bit more about that. We're built upon the x86 ecosystem. Intel is a partner of ours, an investor, and we've built upon really the most pervasive architecture, as I think has been demonstrated on by the top 500 lists as well. And our approach here has been able to take reconfigurable fabric, FPGAs, and use that as a coprocessor to the x86. And the goal here being to deliver higher performance in an application-specific sense, and the byproduct of that is very high efficiency in terms of power utilization and data center footprint and whatnot. So the final bullet here, we talk about an experienced team. So some of your subscribers will remember Convex Computers, and that company that started out making mini supercomputers back in the 80s to fill a gap between VAXes and Crays, and went on to be acquired by Hewlett-Packard in the mid-90s. It's the same founding team. So myself, Steve Wallach, and Tony Brewer are the founders of Convey, and we about 85% of our staffing at this point are people with that had Convex in their background. So people that have been around high performance computing and built really the architects of the Convex systems, and what has been, what eventually, after the Hewlett-Packard acquisition, was the high end of their product line, Superdomes and whatnot, was designed by the team here. So just a little more on our investors. The company's been around since we founded it in 2007, and both Intel and Xilinx are strategic investors in the company. And then we have support from some of the most well-known venture capital firms as well. So we'll move to the next slide. So a little bit more about hybrid core computing. So on the left in the top there, you'll see a bunch of what we call application-specific hardware, and this can be typified by maybe PCI plug-in boards that either do have FPGAs or GPUs on them, and you can easily plug these into a system, but then you're immediately faced with some of the programming challenges associated with that. And of course, down to the right, we've got this ubiquitous x86 architecture that is easy to program as long as you're not trying to get huge efficiencies out of scaling a program multi-core and whatnot. So our idea was to marry the two, but keep the best of both, which is application-specific performance that you get from specific hardware with the ease and deployment and programmability of the x86 infrastructure. So the next slide talks a little bit more about how our hardware is architected. So we begin with basic building block in HPC these days, which is a two-socket system. And this is, of course, most of the systems on the top 500 start with these platforms. that usually have two x86s populated with some amount of memory. What we do is populate one of the sockets with an x86, and the other socket is where our coprocessor plugs in. And the coprocessor becomes an integral part. We ship a complete system, and that coprocessor has a number of FPGAs, but four of the largest are the computational engines, or application engines as we call them. So, that's kind of the, one of the fundamental, design criteria here. And the second was if you build a system that's got a lot of computational capability, one of the next bottlenecks you usually run into is how do you feed something that's that hungry. So we built, a memory system in this kind of a CC NUMA environment that we've all become familiar with, where the memory system itself will support, a peak of 80 gigabytes a second, so about tenfold what the Intel system has here. And very uniquely, we implement this based on technology that Intel has licensed us. They're both their front-side bus and QuickPath interconnect, so that we can implement cache coherency and virtual shared memory. So, why did we do that? Well, this really enables a unified programming model, such that you don't have a development environment for the x86 and a development environment for, something else. We have one set of compilers and tools, and it's implemented on top of, the safety of a virtual memory system. And then, to top that off, we've built the memory system with the capability of having a scatter-gather capability, and we'll describe the benefits of that here coming up. Slide 5, or the next slide, a little bit more about the inside of this neat little coprocessor we built. Is we've got the four application engines, and we have actually two versions of the platform in production today. One that's built on Xilinx's Vertex 5 technology, and another one that's built on their latest, we'll call it Moore's Law progression, which is the Vertex 6. And those all, talk through a crossbar to this memory system that has 8 memory controllers, and each memory controller, controlling 2 DIMMs. And those DIMMs can be either a standard off-the-shelf, DIMM, server DIMM, or, a custom one that we make that does the scatter-gather. And then there's, in the blue box up to the left, is a section where we actually interact with the host and cache coherency protocols. And there's the scalar processor that does instruction fetching and decoding and dispatch. So let's move on to the next slide. We talk about some of the performance. So this memory system that we built, and what I've contrasted here is in the blue lines is the performance of our scatter-gather memory DIMMs in the system. And the benefit of scatter-gather, as you're aware, is that you can address any 8-byte quantity or 164 bit word on every clock cycle, independent of cache lines. And so on the bottom, the red line there is showing what happens on a Nehalem or Westmere type of system, where if you're using every byte of every word of a cache line, you'll get roughly 15 gigabytes a second on the famous Stride C benchmark 3C that Mark Seeger had built. And then once you get outside of a stride of 1 and into the worst cases beyond 8, so you're only using 1 word per out of a cache line, your performance of a cache-based system drops substantially. And in this case, it's you'll drop to about 400 megabytes a second when you're only using 1/8 of the memory accesses. Worth mentioning here, so we've got also something that we borrowed from that Burroughs had introduced a couple decades back, which was the idea of using a prime number interleave on the memory system. And this is good. So most memory systems are built on the a power of 2 interleave scheme, and you'll quickly find out if you're accessing a memory that is a power of 2, you run into bank contention and your bandwidth falls way off. So by implementing a prime number interleave scheme, you smooth out all the accesses, and the net there, as you can see in the blue line, is we can sustain 48 gigabytes a second on this benchmark, except when you hit the power of 31, and which is the prime number interleave. And then that's the only point you get bank contention. And anybody who's worked a lot with FFTs, that like to be dimensioned in powers of 2, understand what the benefit of this would be. And then the next slide, just another illustration of the benefit there, which is, here's on the far right, Westmere system, 1 core that's, on this benchmark where you're, highly, where your interleave or your stride is greater than a cache line. You get that 400 megabytes a second, and then 12 cores can get a little better utilization. They can get a total of 3.9 or 4 gigabytes a second, and that would be out of a total of about 40 gigabytes you get with a standard platform that's available with those systems. And then you can see how our platform can sustain roughly 40 gigabytes a second. So all this is really useful information or background, I think, for what we're going to talk about next. In the latter half of the presentation, about how the system is really uniquely suited for types of problems, and in particular, I'm sorry for the buzz there, a phone call coming in, but for the benchmarks like the Graph 500. Okay, so the next slide, titled Hybrid Core Computing. So I've described what this coprocessor is. Now let's talk about some of the benefits of it here. And so now that you've got this reconfigurable fabric, it gives us the ability to build any kind of instruction set architecture that we like, or we think that we or customers think can provide performance benefits. And indeed, we've built instruction set architectures around areas of life sciences, financial analytics, oil and gas, and this area we call data intensive. We call these personalities because these can be dynamically loaded, so that when you load a personality, it takes on that kind of application-specific capabilities for the platform. Importantly is, we have a set of compilers and debuggers and profilers that allow you to utilize this instruction set architecture, both x86 and these personalities, and ultimately applications taking advantage of it. So next slide, using personalities, we a little more details about how our programming tools help. We started with the Open64 compiler suite and used the front ends from that, the C, C++, and Fortran, and then built optimizers and code generators based on whichever personalities we define. And these are dynamic in terms of we're continually developing new personalities for new market segments. And then the compiler is able to understand what those instruction set architectures can do, and then generate code. In fact, at the end, we generate a fat binary, and that fat binary can, in the simplest terms, you can run it on any x86 architecture, and it just runs normally because we've got a full copy of the x86 version of the app. But when you dispatch that binary on our platform, that executable begins to dispatch instructions to the coprocessor. So a nice seamless development and deployment model. Okay, so let's talk about Graph 500. This week we issued a press release about some of the performance achievements that we've been able to achieve, and then talk about this in the context of data-intensive computing. So the first bullet, given that we've got an architecture that's basically infinitely flexible in terms of defining instruction sets, not only what can we do, but what can we do that takes advantage of the strengths of this architecture. And then over the right, there's a number of bubbles. When you've got an architecture with a memory system like we do, and it lends itself to sparse matrix vector operations, search and data mining, n-body physics, graph theory, for example. And then, our goal is to implement these such that it natively meets, the requirements of market segments. And we'll talk about that a little bit more coming up. So the next slide is just a real simple explanation for everybody, just to make sure we're all on the same page of what is a graph. And I've shown a graph about interactions with people, and you can think about this in terms of a Facebook or LinkedIn kind of a model. Here you can see Peter knows Amy, and Peter knows Josh. Of course, Amy knows Josh as well, and Sarah knows Amy. So these connections can be built, and quickly as it scales becomes a huge graph with the arcs being the interactions between people, and those arcs can have characteristics. How well do you know someone? How close a friend you are? And we'll talk about other applications of that next. And this next slide. Borrowed from David Bader at the Georgia Tech, and he talks about some of the work that they've been doing in terms of really large petascale work around large-scale data analytics, and three main areas to look at on this slide. Astrophysics. Well, you think about the bodies in the universe. It becomes a pretty large graph with the arcs being the gravitational interaction between these heavenly bodies. Bioinformatics, an area that we'll not go into much detail here, but an area that we've got a really good footprint in, where people are doing drug discovery, genome assembly. Each trying to sequence these becomes a large graph problem very quickly. And of course, we've already talked a little bit about social analytics and informatics, but you can think of some of the utilizations of that would be, in terms of what happens if there's a disease outbreak, and hopefully there's no more E. coli impact over there in Europe, but who can be affected by things based on where they've eaten, or who they've been around in terms of potentially infecting someone. So there's a lot of very practical usages of large-scale graph analytics. And indeed, the next slide, one that a critical one around people doing surveillance and intelligence, or terrorism detection using graphs. You think of the an example here is Krebs did a analysis of the 9/11, where he looked at all the pilots of the planes that that actually participated in the event, and then was able to map back that and build a graph or a network of that terrorist network from there. And this was all done from publicly available data on the web. And so you can think about how would you not do this in a post-mortem sense, but how would you do this proactively to prevent terrorism from impacting us. So a lot of really important and vital usages of graphs. So next slide, we'll talk about so what are some of the processing characteristics when you're working with graphs. Well, there's lots and lots of non-sequential memory accesses, and so So the first thing you learn is cache-based architectures, immediately, suffer, bandwidth limitations based on, these non-sequential or strided accesses. The second thing that happens is there's a lot of atomic updates, and as you try to build out solving a graph problem in a distributed manner across multiple domains or coherency domains, you run into bottlenecks in terms of doing these atomic updates, network overhead and locking overheads. So these are some of the challenges that people in the graph analytics area are working hard to overcome or understand how it impacts performance. Other than that, it's an extremely parallel application. So let's talk about a little bit more about why someone might be interested in it beyond some of the usages we've already talked about, and that's on the next slide. So social network analytics, there's an awful lot of commercial utilization today of this around brand awareness, targeted marketing, supply chain logistics. Just by simply doing web searches and building a graph of interactions or references, you can learn an awful lot about a topic. And then indeed, one of the analysts, Gartner, has looked at how pervasive the utilization of this technology is within retail and manufacturing companies. So you can see here most of the large companies are already investing in digital marketing of some sort, and then most rank it as just to understand how people view their brand or their in terms of a sentiment as the most important use of tools like this. And of course, many people today have cited there's a big gap in the tools for social network analytics, and it amounts to about 35% of the IT spend in these areas today. So that's another reason why it's an important area for us. Not just that there's a Graph 500 benchmark, but there's a large market footprint using social network analytics today. Okay, so on to what we announced. So yesterday our press release talked about one of our systems, which is a single node, a 2.5U platform, our Convey HC1EX platform, on a size 27 problem, achieving a performance of 775 million edge traversals per second. And you can see now there will be a new version of this Graph 500 that comes out next week, and certainly our ranking will adjust in whatever the results of that is. But here's how our ranking compares versus what was published in November. For instance, you can see another system on there that had done a size 27 problem, being the Jaguar machine at Oak Ridge, achieving about 800 million edges traversed per second, and that taking 512 nodes. And you can look up and down the list here and see there's a lot of very large systems that has been taken to solve these problems. And so I hold out for you and your subscribers that this architecture being really powerful in as much as you can build application-specific instruction sets, coupled with a very high-performance memory system. It's remarkable that a single node 2.5U system can achieve this level of performance. And so I'll finish up here with my slide set, just talking about one of our mantras. It's balance. When we create competing systems, going back to our convex days, and our belief here at Convey is you've got to not only address compute, and we address that, we think, with a pretty novel way to build highly tunable solutions to a problem using this reconfigurable fabric, but coupling that with a system that has very high bandwidth and a smart memory system. So I'll end with that, and entertain any questions you've got, Rich. That's correct. We provide a Linux based on CentOS. Yes. So we've got we provide compiler tools. We provide libraries, and in some cases, full applications built on top of this. So you can think of in some of our personalities, we've got for a couple for example, a single precision vector personality. There, it's you take your program and compile it with our compilers, and it generates x86 and vector instructions for the coprocessor, and then you just run it. So the fact that you've got a FPGA-based coprocessor is completely transparent to you, and that's our whole goal. In other cases, we've built libraries, math libraries based on, similar to MKL and FFT libraries, and even higher level libraries around, a Smith-Waterman search, for instance, where you would, it's a function call type of a library where you could say call Smith-Waterman to, search, a 64 gigabyte a chunk of data, if you will.
So going back to your slide 17, Bruce, I think it's just remarkable. If you've got a 2.5U node, a single node, right, performing essentially the same as a 512 node Cray XT5. Do you have any idea what that Cray would cost? That would be in the millions, wouldn't it?
Yeah, our estimation is that's probably about between a $2 and a $3 million platform.
Wow. So I was going to ask you about the customers.
So if you look at the list there, you'll see obviously a lot of national labs on this list, and the next list I imagine we'll see more users. But what you don't see here, and this is typical, you probably won't see some of the major let's say internet search providers that have the same kind of problems, fraud detection. So there's a lot of people that are using graph technology that will identify with the capabilities that are talked about here around Graph 500.
And is there any kind of Moore's law as you look out into the future, like where your performance is going? Is there a way to map that, Bruce?
Well, we like to think Moore's law works a little more to our advantage in terms of using reconfigurable fabric. So I'll give an example is when we went from our HC1 platform and introduced an HC1EX. So that was really a Moore's law jump that Xilinx made, and we got over 2.5 times more performance in that jump, and it really fell to the bottom line. And so I think you'd be hard pressed to see that kind of benefit falling out from Moore's law in terms of more and more cores being put on a processor die. It's not completely fair. We've got the reason why we can achieve that is we've got a memory system that's sit there ready to take advantage and to feed a large amount of processing, and memory bandwidth always becomes a bottleneck at some point, and we'll continue in future architectures to drive performance around our memory subsystem, and you'll see us introduce even really innovative memory architectures in future generations. So any of your subscribers that happen to be at ISC next week and are willing to stop by and sign an NDA, we'll give you a peek under the covers of what's to come.
Well, that sounds great, Bruce. Hey, I really want to thank you for coming on the show today, and would love to meet you in person when you get here. So look for the red hat. I'm easy to find.
Will do, Rich.
All right, folks. Well, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.